We introduce iShapEditing, a novel framework for intelligent 3D shape editing based on diffusion models. For a given shape, users can simply click on handle points and their corresponding targets. Our method will accurately move these handle points to their respective targets while preserving plausibility. iShapEditing offers a wide range of capabilities for various drag-based editing tasks. It provides users with an intelligent editing solution that eliminates the need for tedious editing processes. Let's begin by defining our problem. Given a specific source shape and user input information, our objective is to generate an edited shape satisfying the following requirements. Firstly, the handle points should precisely align with the target points. Secondly, the edited shape should be realistic and preserve a reasonable level of semantic consistency with the source. Traditional methods typically treat shape editing as a constrained optimization problem. However, these methods often lead to the generation of unrealistic shapes due to their lack of comprehensive semantic understanding of the object. Recent research has extensively explored data-driven strategies, particularly leveraging deep learning techniques. However, existing methods often lack user-friendly features, which can pose challenges for users seeking to intuitively edit shapes. Therefore, this paper aims to address this gap by presenting a framework tailored for intelligent shape editing. We have named our approach iShapEditing, signifying intelligent shape editing. Our work leverages a pre-trained generative model and controlled generation strategies. It gives rise to two primary inquiries: the selection of a suitable 3D generative model and the integration of user-supplied editing signals into the shape generation. Triplane representation, which combines the strengths of both explicit and implicit representations, has emerged as a promising alternative. Consequently, our approach utilizes the triplane diffusion model for high-fidelity shape generation and editing. We utilize strong feature correspondence and a classifier guidance strategy to guide the generation of edited shapes that meet user-defined constraints. To generate a shape, we initiate the process by sampling the latent code. Subsequently, we iteratively apply diffusion forward to acquire the triplane representation. This representation is then fed into the triplane decoder, resulting in the final generated shape. When incorporating user input, we copy the latent code and pass it through the init. By leveraging strong feature correspondence, we establish a classifier function between the features of the source shape and those of the edited shape generation. We then utilize these gradients to adjust the noise representation at the next time. Continuing in this manner, we ultimately obtain the edited shape that satisfies user requirements. Handling user-supplied 3D real shape differs from editing generated shapes as it entails obtaining its corresponding triplane representation and employing the diffusion inversion algorithm to derive the latent code. During the sampling process, one can derive the predicted triplane representation at each time step, which subsequently feeds into the triplane decoder to obtain the predicted shape. This process enables the establishment of a loss function between the predicted shape and the ground truth. By employing the classifier guidance strategy, we can guide the noise representation at the next time. The triplane representation obtained in this manner stays on the learned triplane manifold and can be utilized for subsequent inversion and editing. We depart from traditional DDIM-based inversion algorithms and instead utilize a DDPM-based approach for triplane inversion, which recent studies have shown to be more effective. Specifically, we utilize the DDPM forward formulation to derive the intermediate noise representation at each time step. Feeding this representation into the unit enables us to extract the features. Proceeding in this manner, we obtain the final latent code. With these feature sequences and latent code, we proceed to edit the real shape by establishing feature correspondence following the previously discussed dragging strategy.
In our system, users begin by selecting a generative model and generating a random shape by clicking the Create Mesh button. Subsequently, users define the desired edits by selecting handle points and their corresponding targets on the interface, followed by initiating the editing process with the Start button. Our method accurately adjusts these handle points to their respective targets, while ensuring the plausibility of the resulting shape. In one instance, a real car shape is selected, and by clicking the inversion button, its corresponding latent code and features are obtained. Subsequently, appropriate handle and target points are selected to achieve the desired edits. For instance, we successfully moved the crossbar at the top of the car. We demonstrate the editing of an airplane. We effectively elongate the airplane's tail. For additional examples and details, please refer to the supplementary PDF file provided.